fillers class, then this is who I am. This is our session. And I will be going over problems from the end of chapter 6 all the way to chapter 10, so moment of inertia and frames and machines. And the solutions to this will be posted on my WordPress site. You can see that right here. I'll scroll up a little bit for those of you who aren't here in person. Okay, so go ahead and write that down if you want to. If you are in fillers class, it is posted on web courses on my SI Times page, so you can get it from there also. Is anyone writing it down? So I may move on or not. No? Okay. Yep, sure. Do you need to take a picture of it?
No, you said that's on course?
Yes. On our website. Okay. So let's go ahead and get started with the first problem. Okay, can everybody see this fine? Yes? No? Okay. So what type of problem is this? Okay, yeah, awesome. So it's a frames problem. Okay, so what is this asking us for?
The horizontal components of pins B and C?
Yeah, so the horizontal and vertical components of force at pins B and C. So looking at a problem like this, can we solve for any of those unknowns just like it is? Okay, no, why can't we? Because there's too many what? Unknowns. Yeah, because there's too many unknowns, so how many unknowns do we have? Okay, so we have 5, and how many equations of equilibrium do we have? 3, so what's the most number of unknowns we can have? Okay, awesome, so how do we get to only 3 unknowns? What was that? I hear 2 force member, what was that? Huh? Oh, so the y force? Uh-huh. So what can we do to this problem?
We have to break it apart.
Okay, awesome, break it apart. So which part do we want?
That's the B, C, D, and the bullion.
Okay, awesome. So if we have B, C, how many unknowns will we have?
Well, 3 if you consider that B, A, B is a 2 force member because of the 2 pins. So
Okay, awesome. So if we look at connection A, B, we can see that that is a 2 force member. So the 2 reactions that would be at B can be replaced as 1. So then how many unknowns will we have? 3, awesome. So can we solve the problem like that? Yes, awesome. So I'm gonna go ahead and draw the free body diagram of member BC. So we have our pulley right there. So what goes here in here? What can we label it as? What was that? Okay, so 75 kilograms? Is that what weight is in terms of? Yes. With units? Okay, awesome. So we can call it W, so it's weight. And how do we find the weight? Okay, awesome. So mass times gravity. So we can say W equals mg. The mass is 75 kilograms. And gravity is 9.81 meters per second squared. And then what will that give us for the weight? 735.75 what? Is it pounds? What units is it? What's that? Newtons. Okay, so we have weight is 735.75. I'm just going to leave the W right here. Okay, so what do we need at the left part of this free body diagram?
it's a pin, so X and Y components.
Of what?
Let's see.
Okay, awesome. So we need the support reactions, so CX and CY, and anything else. What was that? Okay, awesome. So we need that 2 force member right here, and we can call that FAB. Now, what goes on this triangle here? Okay, awesome. So the lower part of the triangle, what dimension should that be?
2 meters.
And for the height? Awesome. And for the hypotenuse? Okay, awesome, 2.5. Now, is there anything else we need to label on our free body diagram? What was that? Is that good? We also need the distances. So from here to here, it's 2 meters. And from there to there, it is 0.8 meters. Okay, so with this free body diagram, how can we solve for any of the unknowns?
Some moments about C.
Okay, awesome. So if we take some moments about C, what can we solve for?
FAB.
Awesome, solve for FAB. Now, what do you want our positive orientation to be? Conventional?
Yeah.
Okay, so counterclockwise. It's always a good idea to include that so that way the professor knows what your thinking was. Okay, so how many components should we have in our equation?
3.
Okay, awesome, so 3. So let's start with FAB. Now, does FAB have a horizontal and vertical component in this equation?
Not this equation.
Okay, so which one isn't in this equation?
The horizontal.
Okay, awesome, so the horizontal isn't going to be in this equation, and why is that?
Because in the line of action of the moment.
It's awesome. So its line of action passes through point C, so its perpendicular distance would be 0, so it would cancel out. Now what about the y component? Would that be positive or negative?
Positive.
Okay, awesome. How do you know it's positive?
Because it's on the line of
Because it agrees with our convention. Now for the y component, what do we need to do with that little triangle?
It's going to be ratio, so it's going to be 1.5 over 2.5.
Does everyone agree with that? I'm gonna go with yes. Okay, and then we need to multiply it by its perpendicular distance, which is 2 meters. Okay, now let's start with this W right here. Is that going to be positive or negative?
Negative.
Awesome, and why is it negative?
Because it's against our convention.
Okay, awesome, so it goes against our convention. Okay, and what is its perpendicular distance? Awesome, 2.8 meters. And then what about this W right here? Awesome, so it's positive, so it agrees with our convention. And then what is its perpendicular distance? Oh, we forgot that little distance right here. Awesome, so 0.3 meters. Now, is that everything that we should have in our equation?
Yes.
Okay. Now I'm gonna go ahead and just write this down here. Now, what was W again?
735.75 meters.
Awesome, so 735.75 is 2.8. And then times 0.3. Okay, now if you solve for FAB, what will you get? So 18 something? Did anyone else get that? Okay, so somebody got 6,000, somebody got 1,800. Anyone else?
I got just about 1,500.
1532?
Yeah.
Okay, so it is 1532.81. And what unit should this be? Awesome, newtons. Okay, so now we solve for FAB. Is there anything else we need to solve for now? Okay, awesome, so support reaction. So how can we solve for them?
We can do moments about B.
Okay, awesome, we could do moments about B. Is there anything else that might be simpler? Okay, awesome, so some moments with the X and the Y, we don't have to worry about those perpendicular distances. So let's start with, so how many terms should we have in this equation?
For X, only 2.
So I heard 2 and I heard 3.
3.
So which ones?
So CX,
Okay, so CX we listed as positive, so we'll leave that as positive. What else?
positive FAB.
Okay, so we have FAB, and how do we get into its X component?
2 over 2.5. 2 over 2.5.
Okay, so 2 over 2.5. And then what else should be in our equation?
Negative W.
And then minus W. Okay, so we have Cx is equal to 735 plus 75 minus FAB, which was 1532.81. It's 2 over 2.5. So then what will we get for Cx? Okay, so negative 490.5. And what units? Newtons. Awesome. So what does that negative sign mean? Opposite of what? Okay, awesome. So opposite of our convention. What was our convention? Awesome. So positive to the right. So this means that it is actually going to the left. So we can just draw a little left arrow. Now, is this one of the things that we were trying to find? Yes, so go ahead and put a box around that. Okay, so then what else do we need to solve for?
Support reaction CY.
Okay, awesome, so CY. And then what equation should we use?
Sum of forces in the y direction.
Awesome, so sum of force in the y is equal to 0. And how many terms should we have in our equation?
3.
Okay, awesome, so we have CY, since we list it as positive, we leave it as positive. What else?
FAB.
FAB, is it positive or negative?
Positive. 1.5 over 2.5.
Okay, so 1.5 over 2.5 give you its vertical component. And then what else do we have?
Minus W.
Minus W. Okay, so if we try to solve for CY, be W minus FAB, 1.5 over 2.5. W is 735.75 minus 1532.81.
Negative 183.936.
What did you get? 183.94?
Negative 183.936.
Okay, so we get negative 183.94 newtons. And what does that negative sign mean?
It means that it's opposite of our convention that we thought, the direction we thought it was the same convention.
Okay, awesome. So that means it's opposite of our positive, or our convention. So which way is it actually going?
Down.
Awesome. And now, is this one of the things we were trying to find? Yes. So go ahead and put a box around that. Okay. Now, have we solved for everything that the problem is asking us for?
No, we still have to split FAB, that will essentially be the X and Y components.
Okay, awesome. And why do we have to split FAB into its X and Y components?
Because that's the one.
Awesome. So it was asking for its vertical and horizontal components. Okay. So if we were to solve for the X component of FAB, what would it be? So let's call it BX. How do we solve for it?
Just multiply.
What was that? Like this?
Yes. Multiply 1532.81 times 2.5.
Okay, so we have FAB, and then how do we get to its X component?
Multiply that by 2 over 2.2.
Awesome, so multiply it by 2 over 2.5 to get its X component. FAB was 1532.81. And then what will that give you for a final answer?
1226.248.
Awesome, and then what units? Okay,
Beautiful.
and is this one of our answers that we're looking for? Yes, so we will go ahead and put a box around it. And then how do we solve for BY?
Same thing, but just find the ratio for the horizontal or vertical. FAB times 1.5 over 2.5.
Awesome, so 1.5 over 2.5 gets vertical component. Then you have 1532.81. And what will that give us for our final answer?
No, it's 919.686.
Okay, so 919.69. And then it's also in newtons. Now, is this one of the things we were trying to find?
Yep.
Yes, so we're going to put a box around it. Now, is there anything else we need to solve for? No. So I'm going to go ahead and zoom out. So there's that if you need it. Okay, does anyone have any questions about this problem before we move on? No? Okay. Okay, so let me go ahead and move on to shear and moment diagrams. Okay, so we have this problem and it's asking us to find the shear and moment diagram. Now, how do we go about it? How do we start this problem?
I gotta find the diagram. Yeah.
We have to do what?
Free body diagram.
Okay, awesome. So free body diagram of what? What was that? Okay, awesome. So we have to cut it. Now, how do we know where to cut it?
We gotta go through the distributed load. So
Okay, so through the distributed load. Awesome. How do we know it's through distributed load?
what?
How do we know it's through the distributed load?
Because it's uniformly distributed.
Okay, awesome. So it's uniformly distributed. And what is one of the rules for a distributed load?
You mean how will it look on the graph, or?
Like, what is one of the rules for a distributed load for this type of problem? So do we have to cut through it? Is that one of the rules? Okay, awesome. So we are going to make our first cut somewhere. Oh,
Can I bomb the problem you just did?
they'll be posted online.
I just wanted to figure it out back there because I can see very well. So I'll go back to that.
Okay, so this is going to be our cut one. Okay, now, do we know exactly where we're cutting it at?
No. Sorry.
Okay, no. Okay, so what do we do now from here? Yes. What was that?
Can you zoom in?
Yeah, sure. Okay. Okay, so we determined where we need to cut it. Now, what do we need to do next?
So we need to find the external reaction forces first.
Awesome, so we need to find our support reactions, our external support reactions. Okay, so how many will we have? 3. Awesome, so at support A, how many are we going to have?
2.
Awesome, so it's a pin connection. Let's call this AY, and this AX. Okay, and then what about at B? Okay, awesome, so BY. So just one, go and call that BY. Okay, so how can we solve for these?
You resolve the distributed load into one single force. So because of its geometry being a rectangle, you would find that that's the length times the width.
Okay, awesome. So to get the distributed load in terms of force, we can find the area of it, and what will that be? What was that? 320? Okay, awesome. 320. And what units? Awesome, so kilonewtons. Okay, now what do we do? Okay, awesome. So if we take the moment about A, which one can we solve for? What was that? Okay, awesome. So we can solve for BY. And let's go ahead and have our positive orientation. We'll just leave it as conventional. Conventional. Okay. Now, how many terms should we have in our equation? Is it 3? 3 or 4? Let's go ahead and start. Okay, so which one do you want to start with? Okay, awesome. So start with 320. Now, is it going to be positive or negative? And what is its perpendicular distance away from A? Awesome, so 4 meters. And then what about BY? Positive or negative? Guys, can you stop talking, please? Or talk quieter. What was that? Okay, awesome. So the BY, is it positive or negative? And perpendicular distance is 8 meters. Awesome. What else do we need to have in our equation?
There is a moment at C.
Okay, awesome. Moment at C. Now, is that going to be... Let me zoom back out.
No, it's 150. You also have a
The moment is 150. So what do we do with that?
it's a negative.
Okay, awesome. So it's minus, and why is it minus? Okay, awesome. So it goes against our convention. Okay, now do we need to include anything else?
Yeah, the 20 kilonewtons down is
Okay, awesome. So we need to include the 20. Now, is it going to be positive or negative?
negative.
And what is its perpendicular distance?
Is it 11 meters?
Awesome. So 11 meters. Now, is this all of our equation? Is it done?
Yeah.
Yes. Awesome. Okay, so if we solve for by, what do we get? What was that? 206? Yep, 206.25. And what units does it have? Kilonewtons. Awesome. Okay, so we solve for by. Now, how do we solve for ax or ay?
What
was that? Sum of force in the y? And which one can we solve for this way? Ay. Awesome. So how many terms should we have in this equation? Okay, awesome. So 4. So which ones? Awesome. So we have ay. And what else? Is it positive or negative? So minus 320. And then what? So plus by. And then what? Minus 20. Awesome. Okay, so and what was by? Okay, and then what will that give us for ay? Yep, 133.75. Okay, now are we done? Okay, do we need to solve for ax? No, why not? Okay, awesome. So it's in the horizontal force, and when we draw our shear diagram, does the horizontal components count? Or do we take them into account? No, so awesome. Okay, so once we calculate our external reactions, what's a quick way to check to make sure that they are correct and that they make sense?
Well, because the vertical forces up are equal to the vertical.
Okay, awesome. So all the forces going down needs to equal all the forces going up. So one way to check that is to say that ay plus by should be equal to all the ones on top, which is 320 plus 20. So we have 133.75 plus 206.25. Now, does the left side equal 340? Yes. So we say this side is equal to this side, or 340, sorry. So 340 is equal to 340. So that's a check. So this is a quick way to check just to make sure that it's correct, because if you mess up on one of these support reactions, then the entire problem could be off. Okay, so now that we solved for support reactions, what do we do next?
Make our diagram.
Okay, awesome. So draw a free body diagram for what?
Shear.
Okay, awesome. So shear, and what else? What type of free body diagram are we drawing? Okay, awesome. So for cut 1, so we have cut 1 right here. I'm gonna go ahead and put a little color so we can color code it. Okay, so this cut 1 right here that we cut, where is that valid for? From where to where?
From A to somewhere in the middle of that.
So from 0 to 8? Is that what you're saying? Okay, so this is valid from 0 is less than or equal to x is less than or equal to 8 meters. So this cut, we can say, is somewhere along this, but we don't know where. Okay, so let's draw a free body diagram. And put a little cut thing right there. Okay, so what do we need to have on our free body diagram? Was that? Awesome. So AY. And AY was equal to 133 kilonewtons. Okay, what else? Okay, awesome. So we have our distributed load. Okay, now, do we know this distance right here?
We don't.
Okay, so no, we don't. So what can we call it?
X.
Awesome, so we call it some arbitrary distance x. Now, for the distributed load, how do we calculate the force from it? Okay, awesome, 40 times x. And how do you know it's 40 times x?
That's the height of it. The height is 40.
Okay, awesome. So to calculate the area, it's length times width. The length is x, and the height would be 40. So, and where is this 40x located on this beam? Okay, awesome. So halfway in between. So we can call this x over 2 and x over 2. Okay, so what else do we need on this beam? Okay, awesome. So shear, moment, and normal force. Okay, so what is positive orientation for the left cut section for shear, up or down?
Back down.
Awesome, so down. Let's call that V. What about moment? Awesome, so counterclockwise. And what about normal force? So normal force to the right, and what is the normal force equal to?
0, 0.
Equal to 0, so we can just leave that there. Okay, so where do we go from here?
Find dx.
What was that?
Find dx. Make an equation of 2x.
So you're saying find the shear equation?
Yeah.
Okay, awesome. So how do we solve for the shear equation?
Forces in the y direction.
Awesome, so sum of forces in the y direction is equal to 0. Okay, so what should we have in our equation?
AY.
Okay, awesome. AY. Okay, so minus 40x, and then what? Minus v is equal to 0. So what would that give us for v? Okay.
Is equal to
So 133.75
x plus 1
minus 40x.
175.
Awesome. And what is the shear equation? What should the units be? Awesome, kilonewtons. Okay, so now we have our shear equation. What should we do now? What was that? So the moment, okay, awesome. So we also need our moment equation, but what should we do with our shear equation now?
Find the points at 0 and 8.
What was that?
Find the points at 0 and 8.
Awesome, so find the points between 0, or the shear at point 0 and 8. So let's say at x equals 0. What will that give us for shear?
133.75.
So that gives us 133.75 kilonewtons. Awesome. And then at x equals 8 meters. What will that give us for shear? Negative 186.25. Okay, now is there anything else we need to do with our shear equation?
We find where shear is 0.
Okay, awesome. So we need to find where shear is equal to 0. And why is that important?
We'll have to find the peak of the gravity center.
So it'll help us find the max bending moment.
Yes.
So max bending is where shear is equal to 0. So how do we solve for that?
Make the equal to 0.
Awesome. So let's make v equal to 0. So we have minus 40x. And what will that give us for x? What was that, 3.34? So 3.34 meters. So we can come back to that later. Okay, now what do we need to do? Start graphing?
Well, we can continue the cuts and then we'll graph it all. Yeah.
Do we have any other equations we need to solve for this cut?
Moment. The moments.
The moment equation, yes. Okay. And how do we solve for the moment equation?
We could integrate the shear.
Okay, awesome. So we could integrate the shear equation. What else could we do?
Solve for the moments.
Okay, awesome. So solve for the moment. And what equation do we use?
Some of the moments about.
At A or at the cut section? Awesome. So take some of the moments, and we'll have our positive orientation as that. Okay, so what should our equation be? What was that? Okay, awesome. So AY, and will that be positive or negative?
Negative.
So we have negative 133.75. And then what is its perpendicular distance? Awesome, so x. And then what else should we have in our equation? Okay, awesome, so 40x, and is that going to be positive or negative? Awesome, so positive. And then what was its perpendicular distance? So x over 2, awesome. And then what? Is that it? Awesome, so plus m. And is that it?
Yeah.
Yes. Okay, so if we solve for m, what should our equation be?
20x squared. No, negative 20x squared
So negative 20x squared,
plus 133.75x.
so plus 133.75x. And what unit should this be in?
Kilonewton.
Awesome, kilonewton meters. Okay, so what do we do with this equation?
Do the same thing at x equals 0, find the moment, and then at x equals negative, find the moment.
Okay, awesome. So at x equals 0, m is equal to what?
0.
Awesome, so m equals 0. And then at x is equal to 8 meters, what is m equal to? So negative 210 kilonewton meters. Okay, now do we need to do anything else with this equation? Okay, awesome. So find the moment at 3.34 meters, which will tell us what? Awesome. So for max bending. So you could say for max m is equal to 133.75 times 3.34 minus 20 times 3.34 squared. And what will that give us for m? 223.613. Okay. Now, where do we go from here? Okay, awesome. So can we graph this? Yes, no?
Yeah.
Okay. So we have V right here in terms of kilonewtons, and then X is in terms of meters. This is our moment. Okay, so let's start with our shear diagram. So at this point, what should our shear be? So 133.75, does everyone agree with that? Okay. So we'll start right here, and we can label it 133.75. Now, where do we go from here? Okay, awesome. So we know somewhere around here at x equals 3.34 meters, it's 0. But what should that be? How do we get through that point? Okay, awesome. So it's linear. Now, is it going to be straight down, straight up, or diagonal? Diagonal? Okay, awesome. How far down?
Down to negative 186.25.
Okay, awesome. So down to negative 186.25. Okay, now where do we go from here? Can we go any further? What was that? So we can tell based on the figure that was given to us in the problem, but with these equations, can we tell that far yet? No, so what do we need to do?
Keep cutting it.
Awesome, so we need to cut it again. Now, where should we cut it next?
B and C.
Awesome, so between B and C. Okay, and we can call that cut 2. Okay. Now what do we need to do with this cut?
Include everything to the left cut. We're going to include everything from A all the way up to the cut.
Okay, awesome. So we need to include everything up to that cut. So,
The body diagram of the team.
yep, so we can call this cut 2. And what should this be? So over here it was 0 to 8. And what should this be?
0 to 11.
0 to 11? Okay, so should it be from here to here? Awesome, so 8. So less than equal to x is equal to 11 meters.
Yeah, you look at the whole thing. What there is.
Okay. So now we have all the way over here. Now what do we need to include on this free body diagram?
Everything's still to the left of that cut. All the way from A.
Yeah, awesome, so everything, so we still need our AY. And then what else? What was that? Awesome, so we also need BY. Okay, what else? Awesome, so we need the 320. And what is the distance from here to here? Where's it located? Awesome, so this 4 meters. Awesome. What else do we need to include? What was that? So the moment at C. Did we cut before C? So what do we need to label right here? Awesome, so we need to label shear, and shear is positive which way? Awesome, so down. And moment is counterclockwise. And then again, n is equal to what again? It's equal to 0, so we don't even need to worry about that. Okay, so how do we solve for shear?
Some of the forces in the y direction.
Okay, awesome. Some forces in the y direction. And how many terms should we have in our equation? Okay, awesome. So which one? So we have 133.75 minus 320 plus by, which is 206.25. And then what about that v? Is it positive or negative? So minus v is equal to 0. Now what would that give us for our shear equation? What was that? Awesome, so 20 kilonewtons. Now, is this equation in terms of x? No, so what does that mean? Awesome, so it's constant, so what does that mean? Does it vary depending on the distance? Distance x? No, awesome. Okay, and then what do we need to do? So find the moment equation. So we have counterclockwise is positive. Now how do we find the moment equation?
All the distances from the cut. So you have all the forces.
Take the moment at a cut.
Yeah, the moment about the cut is what I'm trying to say.
So you say the moment I cut it?
Yeah.
So would that be positive or negative for that m? For this right here.
Positive.
Awesome, so we start with positive m. What about this 133?
Negative.
133.75. And then what is its perpendicular distance away? Is it x?
8 plus
Yeah. 8 plus x.
8 plus x.
8 plus x? Okay, so this distance right here, from here to here, what is that?
Well, we know it's going to be y is 8. So
Okay, so when we cut it, do we know exactly where we're cutting it?
no.
So that entire distance, what can we call it?
X.
X. Awesome, so go ahead and say from here to there is x. So do we need this distance right here?
So it's 8 minus x?
Is it 8 minus x?
X minus 8.
Awesome, 8x minus 8. Okay, now, is that everything that we need on our free body diagram? Yes, no? Okay, so we have by right here. So we have the 133.75, so what is its perpendicular distance away? So is it x or x minus 8? X. Okay, awesome. And then what's next?
320.
So-
320.
Positive 320. And then what is its perpendicular distance away from x? Or from the end? What was that?
X minus 4.
Awesome, x minus 4. So how do we know it's x minus 4? So we know this distance right here, that's x minus 8. And then we need to go over another 4 meters. So x minus 8 plus 4 is x minus 4. Okay, and then for the by, is that going to be positive or negative? So minus 206.25. And then what is its perpendicular distance? X minus 8. Awesome. Now, is that everything in our equation?
Yes.
So that's equal to 0 right there. It's kind of hard to see. Okay. Now, if we solve for m, what should that give us for our equation? I'll go ahead and give it to you because it can take a while to calculate. So you should get 20x minus 370. And this is in kilonewton meters. Okay? Now, what do we need to do with this equation? Okay, awesome. So plug in 8 and 11. So at x equals 8 meters, what will m equal? So negative 210 kilonewton meters. And one way to make sure that your equation was correct, if you see that x at 8 meters is negative 210, check back over here at x equals 8. We also have negative 210, so that's one way to kind of check to make sure you're on the right track. Okay, and now we need to find that x equals 11 meters. What does m equal to?
Negative 150.
Yep, so negative 150 kilonewton meters. Okay, so now are we done with this equation?
Yes.
Awesome, so now what do we need to do?
Wrap it.
Awesome, so wrap it. Okay, so let's go back to our shear. Do we have enough information now?
Yeah.
Awesome, so for shear, what was shear?
20.
Awesome, so 20. So what does that mean here?
Go up 20.
Up 20?
No?
Up to 20 what?
Oh, that's not really good.
So at this point, shear needs to be 20. So we come up to here, and this will be 20. Does anyone not understand this? Okay.
It makes sense because it's equal to 20. So
Okay, awesome. And so since there's no x in here, what does that mean? It's constant. So it's constant over to where? Awesome. So over to C. And then what was shear at x, or at 11 meters? What was that? Huh? Okay, awesome. So we have this 20 right here. So what happens to our shear diagram?
goes down back to
So it goes back down to 20, or goes down 20. And then where do we go back at? So then we're back at 0, and what can that tell us?
aim at equilibrium.
Awesome, so it tells us that it's at equilibrium, so that's one way to check to make sure that it's good. So I'm gonna color this. We determined this part from cut 1 in blue, and then cut 2. Was right here. Okay, now let's go to our moment diagram. Okay, so what do we do for a moment diagram?
X equals 0, the moment is 0.
Okay, awesome. So x equals 0, the moment is 0. And what's one way to make sure that that makes sense? Okay, so moment is bending moment, and what is located at A?
Oh, a support.
A support reaction. So can it bend at A?
No.
No. So that's one way to check, make sure that it is 0. Okay, so then where do we go from here?
210 to 210 kilograms per meter.
What was that?
Negative 210 kilograms per meter, 8.
Okay, awesome. And what shape should it be?
Parabolic.
Awesome, parabolic. How do we know it's parabolic?
The equation was the second degree.
Okay, awesome. So if we go back over here, you can see that our moment equation was in terms of x squared, which is parabolic. And also, even looking at the shear, can you use this to tell what the shape's going to be?
Yes.
Yeah, so diagonal down is going to be what? So concave down.
Yeah.
Awesome. So we should go down to where?
210. 210? Yeah.
So we have negative 210 right here. And then what do we do from here? Okay, so based on our equation right here, so we had the 210 at 8. Now what happens at 11 meters? Awesome, so it goes up to 150. What was that?
It's a straight line, not a curve.
Yeah, so you're talking about this part right here? Awesome, so that part's linear. Now negative 150, are we done with this? No. What else do we need to include?
The moment, positive moment at C.
Okay, awesome. So we had a moment right here, and counterclockwise moment will make the graph do what? Go up or down? Awesome. So go up by how much?
150.
Awesome. So go up 150, and then we're back up to 0. Does anyone have any questions about this? You say why would it go up 150? Okay, so we have this negative 150 right here, but if you look back at the problem, we have this couple moment right here, this 150. And if it's clockwise, what happens to our graph? Will it go up or down?
Actually, it's clockwise going to be down because clockwise is the opposite of what the convention is.
Good question. What is the answer to that, guys? If it's clockwise, what happens? Hmm?
Because of the support.
Okay, so it should go up. If you work out problems in your book, you'll see that if it's a counterclockwise moment, it'll go down by its magnitude, and if it's clockwise, it goes back up. And another way to check, if you're ever not sure, where should this end back up at? 0. Awesome. So that way you can tell that it's in equilibrium. So if you're ever not sure, you can use that to kind of help you out there. Okay. Now, does anyone have any other questions about this? Any other questions? No? Okay. So we're going to move on. Yes. So the max bending moment? Awesome. So did we already solve for that? You're saying X? So you're saying this X right here? Well, you're going to have to label it on the exam, so it's always a good idea to calculate it just so you can write it in and get full credit. So we can say at this point right here, X is equal to 3.34 meters. Now, what did we determine this part to be right here? What was max bending? 223.613. Awesome. And I'm going to go ahead and color this. So that was found for cut 1. And then this section was found during cut 2.
So how do we know to do the shear at 0 with the first equation? What if there's multiple shear equations that I guess we could solve for if shear was 0, for instance.
Mhm.
Would it still end up being that, even like like say we did another cut,
Mhm.
and then like the shear equation was like Vx equals, just another linear equation. So we technically put the shear equal to 0 and solve for it, and then would it still come out to be the maximum? Would it always
Yes.
tell us
Okay,
where it's
so
gonna be?
shear is always 0. So wherever shear is 0, max bending is always going to be at that location.
Okay.
So like if you were to put the shear over the moment, this would correspond right down to
Yeah,
here.
I understand that. I'm just saying, like, say if we didn't think to calculate that at that during that cut, and say we went to a second cut, for instance, if the beam would look different, and we had another equation that had a variable x in it for the shear, could we also make that equation, I guess, equal to
So you're saying also solve for shear with that equation?
Yeah.
Okay,
that
so
work for-
So when we calculated the 3.34, this was for the first cut section from 0 to 8. And if you look here, 0 was between 0 and 8.
Yes.
So if you were to do it this cut section, is it 0 through here?
No. I guess I'm saying like I see what you're saying. It wouldn't work to test.
Yeah,
that.
so wherever it crosses at, like whatever cut section that is, that's the one that you have to use.
Okay.
Yeah.
That makes sense.
Okay, any other questions? Yes.
For the moment equation of cut 2,
Uh-huh.
would it also work if we did distance A and the distance x instead of doing the whole portion x and then doing x minus A? Because I thought for me that was counterintuitive.
So you're saying make this distance x?
Yeah, make that distance x and then the other distance A.
I mean, usually when you cut the beam, you're cutting it at some distance, and that distance is the entire distance. So you're saying the entire thing is x. I mean, you can try it that way and see if it works, but this is just the way I've always done it. So I mean, try it both ways, see if it works. Whichever way works best for you, you can use that way. Okay, any other questions? No? Okay. Okay, so now we have another shear in moment diagram. Problem?
No.
So shear moment's not your favorite, huh? Okay. These ones are pretty simple. There's only like 2 cut sections. Okay. So for this type of problem, what do we have to do?
Think hard.
Was that think hard? Yes, definitely. Anything else we have to do? Maybe cry a little bit.
Yeah, external reactions.
Okay, awesome. So find the support reactions, and how many are at A?
2.
Awesome. And AX. And then what about B? Awesome. So 1 in the Y direction. Okay, so how do we solve for them?
Take the moment A.
Awesome. So take the moment at A. And we can have our positive orientation to be counterclockwise. Okay, so how many terms should we have in this equation? Okay, awesome. So 3 terms. Which ones? Okay, awesome. So the triangle distributed load. And how do we find the force of that? Okay, awesome. So we have F is equal to 1/2 base times height. And what will that give us for a value? Awesome. So 36 what? Kilonewtons. Awesome. Okay. So which one do you want to start with first? The triangular distributed load force?
Yeah.
Okay. So should it be positive or negative? And then what is its perpendicular distance away from A?
It's 2/3 from the one.
Okay, awesome. So this is located 2/3 from this distance. So if you're ever unsure if it's 2/3 or 1/3, look at it like this. If it was 1/3 away from A, does it make sense for the centroid to be right there?
Sure.
Does it make more sense for it to be over here?
Yeah.
So that's one way to do it. So say this distance is 4 meters. Okay. Awesome. And then what else? BY, is it positive or negative? And then perpendicular distance? 6. Awesome. What else? Awesome. So minus 6 times what? Awesome. So 6 times 9 is perpendicular distance. Now, is that everything in our equation? Yes. And then what will that give us for By? 33 kilonewtons, yes. And what does positive mean? Awesome, so it means our orientation was correct, so it is going up. Okay, and then what else do we need to solve for now? Okay, AX, do we need AX?
No.
No, but what would it be anyways? Awesome, so it'd be 0 anyways. Okay, so we need to solve for By. How do we solve for By? Awesome, so some moments in the Y direction. Okay, and how many terms should we have in this equation? Awesome, so 4. So which ones? So AY. So plus BY, so we have plus 33. What else?
36.
Minus 36. Minus 6 equal to 0. And then what will that give you for AY? 9. And it's positive, so what does that mean? Awesome, so our orientation was correct. It's actually going up. And then what's a quick way to check to make sure that these values make sense? Awesome, so all of the down forces should equal to all of the forces going up. So then we would have AY plus BY should equal 36 plus 6. And then so 9 plus 33, does that equal 36? Or 36 plus 6?
Yes. They're going to be 42 plus 42.
So 42 equals 42, so that's checked, and that's one way to check to make sure that we are on the right track. Okay, so now that we solved for our support reactions, what do we do now? What was that? Yes, we need to cut it. Now, where do we cut it? So somewhere. Awesome. So somewhere between A and B. So let's just do it right here. Call that cut 1. And then what do we need to do for that cut 1?
Highlight it between 0 and 6.
Awesome. So that'll be between 0 and 6 meters. Okay. And what should we have on our free body diagram?
AY.
Awesome, so we need AY is equal to 9 kilonewtons. What else?
36 kilonewtons. It's 12. Oh, yeah.
What was that?
1 times 12 times.
Okay, so you're saying this entire distance is what? Awesome, so this entire distance is x. Now what do we have on this part? Triangular distributed load, so we have. Now, how do we solve for the height of that triangle? Okay, awesome, so find the slope. Now, how do we do that? Rise over run. Okay, what's another way to write that? So 12 over 6. Okay, so the 12 is from the height, so we have 12 over 6. And then 6 is what? Awesome, so the entire length. And then what do we set that equal to? So the force, okay, so the distributed load. Okay, so let's call that omega. And then what's this entire distance? X, awesome. Now what do we do with this? Okay, awesome, so do the cross, and then what are we trying to solve for? Which value? Awesome, so solve for omega, and what will that give us? 2x, and then that's in terms of kilonewtons per meter, so we can plug in W right there. So then what do we do now? So we're going to write W equal 2x. Okay, so how do we find this force right here? Okay, so 2x times x. Now what type of distributed load is this? So divided by 2. So 1/2 of x times 2x, and what will that give us? Awesome, so x squared. Now, is there anything else we need to include? Awesome, so shear. Shear is positive going which way? Down. And then moment is counterclockwise, awesome. Okay, anything else? What was that? Okay. So which one do you want to solve for first? Awesome, so shear. So which equation do we use for that? What was that? Awesome, so sum of forces in the y direction. Okay, and how many terms should we have in our equation? 3, awesome. So we have positive 9 minus the x squared minus v is equal to 0. And then what will that give us for our shear equation? 9 minus x squared, and then what unit should this be in? Kilonewtons, awesome. Okay, so what do we do now? Awesome, so plug in 0 and plug in 6. So at x equals 0, v is equal to what? 9, awesome. And then at x is equal to 6 meters, what is shear equal to? Negative 27 kilonewtons. Okay, anything else that we need to do? Awesome, so set v equal to 0, and what will we solve for? Okay, awesome, so we solve for the location where maximum bending is. So at v is equal to 0, so we have 0 is equal to 9 minus x squared. What will that give us for x? X is equal to 3 meters. Okay, and then now what do we do? Awesome, so use the moment equation. And then have counterclockwise as positive. And then how many terms should we have in our equation? 2? 3. Okay, so which ones? So we have positive m. And what about the 9? Is it going to be positive or negative? So minus 9. And then what's its perpendicular distance? X. And then what about that x squared? Positive or negative? So positive x squared. And what is its perpendicular distance? Awesome, so x over 3. Okay. And now that's it. So then what do we get for our moment equation? Okay, so we have 9x minus, what is this part right here? So 1/3 x cubed, and this is in terms of kilonewton meters. Okay, so what do we do with this equation? Awesome, so plug in 0 and 6. So at x equals 0, m is equal to what? M is equal to 0. At x equals 6 meters. M is equal to what? Negative 18. Okay, and then what do we do now? Yeah, awesome, so find max bending, and how do we do that? Awesome, so for max m, we have m is equal to 9 times 3 minus 1/3 times 3 cubed. What will that give us for m max? What was that? 18? Positive or negative? So 18 kilonewton meters. Okay, so now are we done for now, for this part? Or for this cut section? Yes? Okay, so what do we do now?
Second cut.
What was that? Okay, second cut. Where do we cut now?
Between B and C.
Awesome, so between B and C again. Okay, so we have cut 2. So go ahead and color code that. And then what should we have here?
Between 6 and
Awesome, so and then 9 meters. So what should we include on our free body diagram?
everything from the left to the right.
Okay, awesome, so everything from left to cut to, or from the left of the beam to this cut section, so we still have AY. And then what else do we have? Okay, awesome, so BY. Okay, awesome, so distributed load. And what can we replace that with?
One single reductive.
Awesome, and what was that? 36 kilonewtons. That was 4 meters. Now what is this entire distance of the beam? X. Okay, awesome. So then this distance right here was 2. Okay, so what else do we need to include? So we have V, positive going down, moment, clockwise, counterclockwise. Anything else we need to include? Do we need this distance right here?
Yes. So x minus 6.
Awesome, so X minus 6. Okay. Now, are we done labeling it? Yes. Okay, so which equation do you want to solve for first?
See shear, so
Awesome, so let's do shear. Which equation do we use for that?
some of the forces in the y direction.
Awesome, so force in the y direction. And how many terms should we have in our equation?
4.
Awesome, so 4. So we have positive 9 minus 36 plus 33 minus V equals 0. And then what will that give us for V?
6.
Awesome, so V equals 6 kilonewtons. And what does that mean? Awesome, so it's constant between where and where? Awesome, so it's constant between 6 and 9. Okay, and then what equation do you want to solve for next? Moment. And then use our positive convention of counterclockwise. Okay, and then, so our M is positive, and then what else do we have? The 9 kilonewtons, is that positive or negative?
Negative.
So minus 9, and then what is its perpendicular distance? Okay, and then the 36, positive or negative?
Positive.
36 is
Yeah.
positive.
And then its perpendicular distance is what? What was that? Okay, so
Plus 4,
so x minus 6 plus 2 is what?
8.
X minus 4. Does anyone need me to explain that again?
Oh, that's a negative 6.
So we have the 36, and then what's next? By, so positive or negative? So minus 33, and then what is its perpendicular distance? X minus 6, and is that everything now?
Yep.
So I set it equal to 0, and then what's our moment equation? Actually, I'm going to calculate that one out again because it can take a while, so you should get 6x minus 54 kilonewton meters. Okay, and what do we do with this equation?
Evaluated at 6 and 9.
Awesome, so evaluate it at 6 meters and 9 meters. So at x is equal to 6 meters, m is equal to what?
Negative 18.
Negative 18 kilonewton meters, and we can check to make sure that's correct. So we get negative 18 at x equals 6, and then back over here at x equals 6, we also got negative 18, so we are good. Okay, and then at x equals 9 meters, m is equal to 0. Okay, now what do we do?
Graph everything.
Graph everything. Okay. Okay, so let's start with shear. Okay, so at x equals 0, shear was what? So at x equals 0, v was 9. So what was that? Okay. So we have 9 right here. Okay. And then how do we get from 0 to 6 meters?
goes down to negative T7. Uniform distributed flow.
Okay, so at s equals 6, what was shear?
Negative 27.
Awesome, so negative 27. Now, how do we get down to negative 27? Is it going to be linear? What was that? Okay, awesome, so parabola. And how do we know it's a parabolic? Because our equation had x squared in it, so we know it's parabolic. Okay. And then this value is negative 27. And then, are we done for cut 1 for this part of the graph? So you're saying right here?
Yeah.
Okay, so that was x equals 3 meters. Okay, and then what? Do we get over our next cut section? Okay, so let's go back over here. Okay, so here shear was constant, so it was at 6. Now how do we get up to that 6?
Straight line, straight up.
Yeah, awesome, so straight up. And how do you know it's straight up?
Because shear is constant.
Yeah, awesome, so shear is constant. So then what is from here to here? To get from this 6 all the way over to the end. Awesome, so straight line. And then what?
Straight down, it goes to 0. Yeah.
And then straight down, because if you look up here, we have that 6, and it goes down 6. Okay? So go ahead and color this in. That was for cut 1.
Do you need to color that in for me? Or?
I mean, you don't have to, but if it helps, I mean, color helps me, so if it helps you, you can do that too. I just like to show it so that way it's clear that this was from cut 2, and like that was from cut 1. Okay? Now, go to our moment. So from over here at x equals 0, so m equals 0, and what's one way to check and that makes sense?
This is support.
Awesome, so we have a support reaction at A, so can it bend at A? Nope, so it has to be 0. Okay. Now, at x equals 6, m was negative 18. How do we get down to negative 18?
It's cubic. So it needs to be negative. So
Is it going to be concave up or down? Okay, awesome, so concave down. And so it's cubic, so what does it look similar to? Does it look similar to a parabola?
yeah.
So kind of, it's slightly different. It's kind of hard to draw, so I'm just gonna, so something like that. And what was our max bending right here? What did we calculate that to be?
18.
18. And then what was this value down here?
Negative 18.
Negative 18. Okay, and then how do we get from here to here?
For the second cut.
Okay, so go to the second cut. Okay, and then at x equals 9, what was moment? 0. Okay, and how do we get from there? Is it going to be linear, parabolic, cubic? It'll be linear. So if you're ever not sure, look back at our equation. It has an x in it, just an x, so it's linear. And then go back up to there. And how do we know that that makes sense? So when we get back up to 0, how do we know that it makes sense to get back up to 0? Awesome, so it's in equilibrium. Okay, and then what distance was this? Or sorry, this distance right here.
3 meters.
3 meters, so you can label it if you want to. Okay, does anyone have any questions about this? No? Okay. Go and move on. Okay, so now we have this problem, and what type of problem is it? Okay, awesome, so centroid problem. Now, which one is it asking us to find? X or Y? X and Y, so you have to find both. So how do we do that? What was that?
Gives the equation that line is we have to find the
Okay, awesome, so use the equation that's given to us, so the Y. And what else do we need to do?
Make a cut.
So draw a differential element. So which way do you think would be easier, vertical or horizontal?
Vertical.
Vertical. And why is it easier? Huh? So try doing it both ways. There's actually an example in the book that does it both ways. So just look at that and you'll see that this way is a lot simpler. It takes a while. Okay, so this is the centroid. And so C is equal to x comma y. Okay, so what do we need to label right here? Dx. So that's our differential element, dx. And what is this distance right here? What can we call that? To here to here. What was that? XY, is that what we said? X bar? Or X squiggly? Okay. Okay, so let's call that X. Okay. Okay, so this distance right here, what can we call that? Y. Now, so for the centroid of here, from here over to here, we have X. Now, for the Y, how far up is that? Is it Y distance to the centroid? So Y over 2. So we can leave that like that. Okay, now what is the equation for X bar? So the integral of A of what?
X, Y, dx.
So we have the X squiggly dA. Now what is dA equal to? Awesome, so we have dA is equal to Y dx. So, yes?
When you use y with 2, because I've done problems where I don't use it.
Mm-hmm.
At the same time I do.
It depends on where the centroid is in regards to your differential element. So we have our differential element right here, and so we're calling this entire thing y. But the centroid is only located right here. Yeah, so it's half the distance up. But this x right here, it's the full distance over. Okay. So dA is equal to y dx. Now what should our boundary conditions be?
So by the way, so that's x bar equals the integral of the area x bar, or is it x squiggly?
X squiggly.
Okay.
What was that? Okay, awesome. So 0 to b. How do we know it's 0 to b? So you're saying, is it because we're calculating x bar? Yes?
No.
No? What does it depend on? Awesome. So it depends on our differential element. So we have, so let me go ahead and do it. So we have this y dx, so we can replace dA with that. So we have xy dx. Now, if we have it with respect to x, our boundary conditions need to be also with respect to x. Okay? And then down here, we just have y dx. Okay. Now, what do we do from here? What was that? Substitute what?
Your y
Awesome. So we need to substitute something else into y in terms of what?
in terms of x.
Awesome. So in terms of x, so we need to get that y out of there. So we have x times what? H over b squared x squared. And that's given to us in the problem. So that's x squared right there. And 0 to b of what? Awesome. So the same thing. X squared dx. Okay, so what can we do to simplify this a little bit? Okay, awesome. So move the constants inside or the outside of the integral. Okay, so we have h over b squared, integral of 0 to b of x squared dx. And then the same thing down here. Sorry, that should be x cubed because we have that x times x squared. Okay, now, what can we do now?
You cancel out the h over b squared.
Okay, awesome. So these can cancel out. And then what is the integral of x cubed? Awesome. So we have x to the 4 over 4 from 0 to b. And then what about x squared? X cubed over 3 from 0 to b also. So we plug in b. So for the top, we have b to the 4th over 4 minus 0. And then on the bottom, we have b cubed over 3 minus 0. Okay? Now, what should we get now? Okay, so if we write it as b to the 4th over 4 over b cubed over 3, how do we solve for that?
3b over 4.
Okay, so that's the answer. But how do we get to that? What's one way to simplify this a little bit? Okay, awesome. So instead of dividing by the fraction, we can multiply by its reciprocal. So we have b to the 4th over 4 times 3 over b cubed. And what would that give us for our final answer?
3 over 4.
So 3b over 4. Okay, does anyone have any questions about this part? No? Okay. Now what do we need to solve for? Okay, awesome. So we need to solve for y bar. So what's the equation for y bar?
Y squiggly.
Okay. So the integral, right? Y squiggly what?
dA.
dA. And then over what?
dA. Integral of
Awesome. So dA. And what is dA equal to?
x dx now?
What is that?
Well, y dx.
So y dx. So we look back over here, dA is equal to y dx. So let's plug that in. So we have y times y. Okay, so that y squiggly, what was y squiggly? So if you look back over here, it's actually y over 2, so half the distance. Okay, and then dA, so dx. Okay, and what should our boundary conditions be? Is it 0 to b or 0 to h? It's 0 to b. Now, why is it 0 to b? Awesome. So our differential is still with respect to x. So if you're ever unsure about which boundary conditions to use, look at your differential. If it's dx, it needs to be your x conditions or your x distances. And if it's dy, then you use your y. So even though we're solving for y bar, we're still using the 0 to b conditions. Does that make sense? Okay. What was that? Can you do dy? Yes. So if we did that, we would have to draw the different differential element, but I'm leaving it like this so that we only have to draw one, and it makes it simpler. Okay, and then what, so we have 0 to b, and then what should be on the bottom? So 0 to b, so yep, y dx, okay? And then what can we, okay, so what do we need to do now?
Actually, would it be 1 dx in the bottom?
What was that?
This is in the bottom dA, so we
Okay, so we have the integral of dA, and over here we determined that dA was y dx. So dA over here should also be y dx.
Oh,
Y
I
squiggly,
see the y squiggly is, yeah.
y squiggly is y over 2.
Yeah.
And that's y squiggly. Okay. Now, how can we simplify? Yes? Okay, so back up here, we determined that x distance was over here. Y distance is this entire length, like the height of the differential element, but this centroid right here is half of that distance. So it's y over 2. Does that make sense? Okay. Okay, so where do we go from here? What do we need to do? Substitute what? Okay, awesome. So we need to substitute into y, and why do we need to do that?
Make it towards x.
Okay, awesome. So in terms of x, and to match our differential. So we have 0 to b, and what is y? H over b squared x squared times again, and then that all is divided by 2. And then what goes on the bottom?
Just integral of 0 to b, h over b squared, x squared.
Awesome, so the same thing, so plug in y there too. Okay, now how can we simplify this a little bit?
All the constants.
About the hb squared.
Okay, so pull out the constants. So we have a 1/2, and then what else do we have?
hb.
HB. So we have h times h, so
Well, h squared.
h squared over what?
b to the 4th.
Awesome, so b to the 4th. And is that everything that we can pull out?
Yes.
So we have 0 to b of what?
X to the 4th.
Awesome, so x to the 4th. And then on the bottom, pull out the constants again. So h over b squared, integral of 0 to b of x squared dx. Okay. Now, what is the integral of 0 to, or of x squared, or x to the 4th? Awesome. So we have x to the 5th over 5 from 0 to b. And then, what's the integral of x squared?
X cubed over 3.
X cubed over 3 from 0 to b. So then we'd have b to the 5th over 5 minus 0. Bring our constants down again. And then b cubed over 3 minus 0. Okay, so can we simplify this top part a little bit? What was that? So what will that give us? So we have h squared. So we have the 1/2 h squared, what? So we have h squared b. Over 5. Okay. And then what about the bottom? What will the bottom simplify out to? So we have 1h. And what about the b's? What happens to the b's? So we have hb. And then what? Over 3. And then what's one way to simplify this a little bit? So we can multiply by its reciprocal again. So we would have h squared b over 10 times 3 over hb. And then what will that give us for our final answer? What was that? Yep, so 3h over 10. Okay, does anyone have any questions about this part? No? Okay. Let's zoom out a little bit. Still copying it down? Okay. Can I move on now? Okay. Okay, so what type of problem is this one?
Centroid once again.
What was that?
Centroid.
Oh, awesome, so centroid again. So how do we solve for this centroid?
Just asking for the y bar this time.
Okay, awesome, so this time it's just asking for y bar. What would x bar be in this case? 0, so do we need to solve for it anyways? No. Okay, so what was the equation for y bar?
Equation for y bar.
So do we still use the integral in this case?
No.
No, so which equation do we use?
I use the sum of the area
Okay,
over
so the sum of, so y squiggly
y squiggly
times the area over what?
the area.
So over the sum of the area. Okay, now how do we find that?
We have to split it up because composites.
So we use the chart?
Yeah, that's what I use.
Okay, awesome, so I use the chart too, so we can go ahead and do that. So what do we need to do to this if we use the chart? Is this a common geometric shape
No.
that we can find the area of?
Separated
Okay, awesome, so separate it into what?
into two rectangles.
To 2 rectangles, so we'll call this rectangle 1, this rectangle too. Okay. So go ahead and write the chart. So segment 1. Okay. So we have the area, and what is it in terms of? So millimeters squared. Awesome. And then, okay, so what is the area of 1? 120 times what?
2. That's 140.
Some 600, and what does that give you? 72,000. Okay, and then for segment 2, what is its area?
240.
So 28,800. Okay, and then we have y squiggly, and what is that in units of?
Same millimeters again.
Millimeters. Okay, and what is y squiggly? What does it represent?
The vertical distance.
Okay, awesome. So the vertical distance from
the
where
base-
to where?
From the base of the bottom segment.
Okay, awesome. So from the base to where?
to the middle of the first.
So where the centroid is?
Yeah.
Awesome. So we can call this one centroid right here, and this one centroid C. Okay, so for segment 1, what is y squiggly?
Starting from 240. So you have 240 to the half of 120.
Okay, awesome. So 300. Does anyone not understand how we got 300?
Say that again. I'm sorry.
Okay. So y squiggly represents from the bottom of the figure, right here, to the centroid of that shape. So we have 1 right here. So we have this entire distance right here, that's 240. But this centroid is located half the distance of this, which is 120, so 60, plus the 240. Does that make sense? Okay. And then what about for 2? Yep, 120. And then, yep, so y squiggly times A. And then what is its units?
Same millimeters.
Millimeters what? Cubed. So we have area times,
right.
yeah. Okay, so 72,000 times 300 is what? So 21,600,000. And then 2,800 times 120 is what? So 3,456,000. Okay, and then what do we do from here?
And you add up the areas.
Okay, so you look back here, we need the sum of y squiggly times A. So what is these, are these two added together? So 25056000. Okay, and then what else do we need?
The sum of the areas.
Awesome, so sum of the areas, and then, awesome, so 100,800. Okay, so what do we do with these now?
Divide them. The y times the area.
Awesome, so we have y bar, so what goes on top?
So y squiggly times the area.
Awesome, so the 2505. And then what goes on, or what units is this in?
Q.
So millimeters cubed. And then what goes on the bottom?
So 100,800.
100,800, awesome.
Squared.
Yep, so millimeters squared. Okay, so what should that give us for a final answer? So 248.57 millimeters. And so always a good idea to write the millimeters, like the units, just so you make sure you end up with the proper ones every time. Now, is this our final answer?
Yes.
Yes. So do you have to use the chart? No, but it can be easier, especially if you have 3 or more members. This one was only 2, but it's still nice to keep it nice and neat. So you can use it if you want, but you don't have to. On an exam, you might be given the chart. So,
Quick question. Can
Yes.
you go over why x bar is 0?
X bar is 0. Okay.
Why is it 0?
Okay, so we have our y-axis through here. So here's our x-axis. Okay, so why is x 0?
They're centered about X.
Okay, awesome. So it's centered. So it's exactly right in the middle. So this in this part, they're both 240 and 120. So it would be located exactly halfway in between that.
Oh.
So if you had your y-axis right here and your x, it would be right at 0, like right at the origin.
Yeah, if it was skewed right or left, like
Right
it
up there,
would, you
then
would have to find
you
it.
have an X point.
Yeah. So depending on where your axes are, it can make it a lot easier or not as simple. On an exam, you might be given like the axes and you have to use that, but if not, you can make them wherever you want. Yes.
For y quickly, where's the distance from? Is it from the base of
hmm From the base.
the base of the
The second segment.
Yeah. So like from right here, starting from right here, so for shape 2, it's halfway of this entire distance, so 120. So we have that 120. And then to get up to here, we have this entire 240 plus half of the 120, so 240 plus 60 is 300. Does that make sense? Yeah. Okay, any other questions? No? Okay. So you're moving on. Okay, the last problem. Okay. I hear a lot of groaning. Okay. Okay, so what type of problem is this? Moment of inertia. Okay, awesome. Which moment of inertia is it asking you to find?
The x-axis.
Okay, awesome. So Ix prime in this case. How do we find that for this type of shape?
Do a large rectangle and then 2/4 of a circle and then subtract it from 4 triangles.
Okay, does anyone get that?
I mean,
Okay, so
yeah.
I'm gonna go ahead and like draw it right out here. Okay, so there's our shape that we have now. So we can split that up into one entire rectangle, so like the entire shape. Okay, so one of those minus 2 of these shapes. So we have with the 45 degree, and then we can add, here I'll write down here, plus 4 triangles.
That's
Okay,
why
does-
I got confused.
Okay, so what are you confused about?
Okay, you see like how you have the 2
Mhm.
times, I'm not sure what shape that is.
So they call it like a semicircular sector.
Okay,
I think, let me
semicircular
see.
sector.
It's here somewhere.
Isn't the triangle part of that semicircular thing?
So the semicircular. Okay, let me get the paper because I have like the back of your book. Actually, can I borrow yours?
Yeah.
Sure. Thank you. Okay. So you have this in the back of your book. So we have a rectangle right here. So we can calculate Ix prime. That's right there. Now, so if we have this entire rectangle, what do we need to subtract from that? So we need to subtract this little shape. But do we have an exact shape like that? No, but do we have one of these?
Yeah.
Yeah. So if we subtract 2 from that, we have to add the 4 triangles. Why?
See, that's why I don't know.
Because okay, so you have this entire rectangle.
Right.
So if you subtract this entire thing, you can't subtract it from nothing.
Oh, you need.
So you
okay.
basically you have to add back to it.
Okay.
Does that make sense?
Yeah. I can make that.
Okay. So plus 4 triangles. Okay. So let's calculate the moment of inertia for a rectangle. Okay, so what's the moment of inertia for a rectangle?
1 over 12.
So 1 over 12.
1 over 12 b times h cubed.
Okay, awesome. So bh cubed, if you're ever not sure, check back here. See that Ix prime is 1 over 12 bx, or bh cubed. Okay, and what is the base? So 200 millimeters. And then what is the height?
The height of it. You have to start from the triangle, right?
So do we actually have a value for the height listed there?
No.
So how do we find it?
By using a triangle.
Okay, awesome. So we can use this right here. So we know that this distance right here is 200. So how do we get the vertical distance?
Sine.
So we do 200 sine of 45. Now why is it sine, not cosine?
Because you want the height. Bring that back in.
Okay, awesome. So think about it like this. When we're trying to calculate the forces, if we want to do the adjacent, it would be cosine of 45.
Right.
But since we want to do the opposite, it's sine of 45. So 200 sine of 45 is just 1. Okay, awesome. So 141.12 now.
42.
Okay, so that distance, is that this entire distance right here?
You have to double it.
Okay, awesome. So we have to double it. So what is 2 times that?
282.8.
Now, are we done with the height now?
Yes.
So we also have to add this 25 and this 25. So what will that give us now? Yep, so 332.84 millimeters cubed. And then what will that give us? A big number. Yeah, so I'll just go ahead and write it out. So something like that. Okay, now we're done with the rectangle. Let's go to this type of shape right here. They call it a circular sector area, so we're just going to call it sector. Okay, so what is the moment of inertia about the x-axis for the circular area?
That's just like 1/4
So 1/4, or the fourth times theta minus 1/2 sine of 2 theta. Fun, right? Okay. Sure. Let's go with that. Okay. So pi of the sector, 1/4, or the fourth, times theta minus 1/2 sine 2 theta. Okay. What is r? If you're not sure, look back at the figure. What does it say that r is? So this distance right here. So what is that distance? 200 to the fourth. And what is theta? Can we leave it as 45? No, what do we have to do? What was that? Awesome, so convert it to radians, and what is 45 degrees in radians? What was that? Pi over 4. Does anyone not understand how to get pi over 4? No? Okay. So minus 1/2 sine, and 2 times theta is what? Huh?
So it's 1.
So can we leave this one as degrees?
No. Yeah. Yes. Yes.
If you want to. Okay, so here's the thing that can be pretty tricky. So this theta right here, you have to convert to radians. This one right here, you can leave it as degrees, and your calculator will have to be in degrees also, but you can convert it to radians. So that way everything's in radians, but you do have to change your calculator to radians once you change it to pi over 2. So I'm just gonna leave it as pi over 2 to keep it, what was that? Yes.
Does that have a reason why?
I'm not entirely sure, honestly. I just know that's how it is.
Both are, numerical way of
Okay.
solving it. If it's just degrees, it's not really.
It's probably not registering as degrees, it's just like some number. So it's probably that. Okay. Now, if you calculate sine over pi over 2, what do you have to do to your calculator? Put it in radians. Yes. Okay, so go ahead and calculate that out now. Make sure you can get the proper answer now, so you know what next year.
Sector, change my calculator to radian.
Yes, but when you calculate the next part, you have to change it back to sine, or back to degrees. Yes, so make a note on like your formula sheet if you have to. Yeah, when you write the formula down. Okay. Okay, so what are you guys getting? 114? What's that? 1 for this entire thing.
Oh, the whole thing?
Yeah. Okay, so make sure you can get this. 265.4 millimeters to the fourth. Okay, now we need the triangle. So now we have the triangle, and what's the moment of inertia about the x-axis for a triangle?
Don't we have to double it for the center?
What was that? Yeah, at the end, we're just calculating it in the beginning.
Okay.
So like we have that right there, but we're just calculating each one, and then we'll plug it back in.
It looks terrible.
Huh?
It looks terrible.
Kind of is. But that's why I wanted to do it, so you guys get this. Okay, so what was it for a triangle? Yep, so 1 over 36. BH cubed. Okay, now what is the base?
You have to find that, so it's going to be 200 cosine 45.
200 cosine 45, and what is that?
Switch back for radians.
Yeah, yep, don't forget to switch back from radians to degrees now, if you convert your calculator.
141,
141, 42, and then the height.
already got that, so that was,
Hmm?
yeah, 332.84.
332? Wasn't that for both of these triangles? So for one triangle, what would it be? Same thing. So sine 45 is the same as cosine 45, so that can save you trouble if you remember that. Cubed, okay. And then, are we done with this triangle part?
Yes.
No.
Yeah.
There's this amazing thing called parallel axis theorem. Not sure how familiar you are with it. What is parallel axis theorem? Okay, so it's plus the area dy squared. What is, so the area of a triangle is what? 1/2 base times height. Awesome. dy, what does that represent? Distance from where to where? So it's from the distance from the x-axis to the centroid. Now, let's look back. Okay, so where's the centroid of a triangle? How do we know where that is?
1/3 from the
1/3 of it.
Okay, awesome. So we know it's 1/3 of the height. Okay, so plus the area of a triangle. So 1/2 times 141.42, 141. So 141.42, and then times the dy. So what is 1/3 of the height? Yes. Yeah. So what's 1/3 of the height? I'll get to it in a bit.
That's going to be 47.14.
47.14. And that entire thing is squared, okay? And then what will that give us for a final answer for the triangle? You're getting 3.3 something? Yes, no? Okay, well you should get this.
111.22.906.88.
Okay, did you calculate all of it? Did you change your calculator back to degrees? Okay, well you should get this number. So. Okay, so this is the number that you should get. Now, why do we use parallel axis theorem for the triangle and not the rest of them?
Instead of using parallel axis theorem, you just do like 2 bigger triangles instead of the 4 really small ones.
I'm pretty sure I've tried it that way and it doesn't work the same because
Then it'd still only be 1/3 of the way out, like that, and then it'd be out.
I'm actually not sure. I haven't tried it that way. So try it and see if we can get the same thing.
Okay.
So it's possible. Okay.
Because it's not centered, and that's the same as the.
Okay, so let's, yes. The 141? Which one? There's like 12. This one right here? Okay, so this is from the base. So the base of the triangle, so we have this distance 200 right here. We need to find this distance right here. So since we have an adjacent angle, it's 200 cosine 45 to get down, and then the height would be 200 sine 45 to get the height. Yeah, okay.
How did you get to 47.14?
Okay, so that is this dy right here. Okay, so dy is the distance from the x-axis to the centroid of the triangle. And to find the center of the triangle, it's 1/3 the distance of the height. Okay. Now, let's say we wanted to use parallel axis theorem for the rectangle.
Wait, so real quick, why don't we use it again for the triangle?
Let's get there real quick. Okay, so for the rectangle, this dy, what's the distance from the x-axis to the centroid of the rectangle?
0?
0. So that cancels out. Now, what about this sector? What's the y distance from the x-axis to its centroid? 0 as well. So,
Oh, I see, because the triangle.
so 0. So if you're ever not sure, just use it every single time, and then you can see when it cancels out when it's 0. But for the triangle, does its centroid lie on the x-axis?
No.
No, so we have to calculate that out. Does that make sense? Okay. Okay, so now going back up here, we have our rectangle minus 2 of those, so by x prime is equal to 1 of the rectangles plus 4 triangles minus 2 of these sectors. So the rectangle was 614. So plus 4 times this. It might. So calculate all of that out, and you should get somewhere around this number. Millimeters to the 4th. Or you can just say, like, round up to 520 times 10 to the 6th, and that looks much better. Okay, does anyone have any questions about this problem? Yes, no? Do you need me to go over anything again?
So you think we'll see something like a mixture of this and the last problem we had?
It's possible if you're with Dr. Filler. I know he mentioned saying something like you'll have a problem and you might have to find like its centroid like from chapter 9 and moment of inertia from chapter 10, so it might be like a 2-in-1 type of problem. It could be that. Any other questions? Yes.
So when do you use the parallel axis theorem in general?
So parallel axis theorem for this type of problem, when the centroid does not lie on the x-axis, you have to use it. Okay. Okay, guys, that's all the time we have for today. These solutions will be posted on my WordPress site. What was that? This problem? Thanks for coming, guys. Was that frames and machine? Yeah, there'll probably be one of those too. Probably. Know how to do it anyways.
Can I see that last answer?
Yeah, give me one second. No problem. I think so, yeah.
Okay.